Well, it's wonderful to be here. I've never been in front of a whole room full of journalists. This is the first for me, and I think this is going to be a wonderful experience. I realized when I was preparing this talk that it's almost 30 years ago to the month that I had my first encounter with a science journalist. I was at the Max Planck Institute for Astrophysics at the time, and I had used the first Cray 1 in Western Europe to do some huge simulations of extragalactic jets. And my mentor, Larry Smarr, who knew the ropes about how science is done and journalism, etc., introduced me to a science writer in Munich. And before I knew it, there was a feature article in the Frankfurter Allgemeine about my work. And ever since, I've interacted with science journalists, and I really enjoy it. I do. Joel asked me to talk about supercomputers, and I guess I'm qualified. I have been using supercomputers continuously for 36 years, during which time computers have grown in power by 1 billion. And what I do for fun is try to ride that exponential, and I've done that my entire career. And that's forced me to move around the world. I was in Germany using an American-made supercomputer because at the time there were no supercomputers in the open domain. They were all in defense laboratories. But eventually the National Science Foundation funded academic supercomputers, and then I came back to the US and was one of the founding research scientists at the National Center for Supercomputing Applications at the University of Illinois. And then I came to San Diego in 2000 to be a professor there. So the title of my talk is Bigger is Better, Trends in Supercomputers, Super Software, and Super Data. However, I'm not going to address super software because I realized last night, listening to all of you, that you really want to know how it works, how simulations are done, what is the methodology. And so I had to cut something out of the talk. So I'm going to skip right over super software so that I can spend a little time on the underlying methodology of computational science. I should say that my primary expertise is programming these supercomputers. My laboratory for computational astrophysics does just that. And if you have any questions about that, I'd be happy to answer them. It is fascinating, it's challenging. I like to say that I've never met a supercomputer that I didn't like eventually. And what I mean by that is they don't work very well when they're brand new. They're a bitch to program, and they're only getting harder to program. But, you know, I like the challenge. So why are supercomputers needed in this field? Well, as Douglas Adams said, the universe is famously large, and it stands to reason that you need a big computer to simulate it. The universe has complexity and beauty on a vast range of scales, shown here from large-scale structure here in the upper right to, you know, an accretion disk around a black hole. And you might ask yourself, how can we possibly understand all of that? Well, the answer is physics. While this all looks like different stuff, you could write down the equations of motion on a single page. And that's what I learned when I was a graduate student, and that was an aha moment for me, and I found that idea so cool that you could do physics inside a computer that I combined that with my love of astronomy and decided to go into computational astrophysics. So don't panic. Here is some of those equations that I alluded to. I don't expect you to memorize these, but these are the equations of astrophysical fluid dynamics, conservation of mass, momentum, energy, radiation energy, magnetic flux, gravity. And these are what are called coupled nonlinear partial differential equations. When I was a graduate student studying computational physics at the Lawrence Livermore Laboratory, I learned how to convert those math equations into numerical equations that you could program up and solve on a computer. And I've devoted the better part of my career to doing that. You add Newton's laws for N particles, self-gravitating particles, and you've got essentially the basic equations that you can use to simulate all of this stuff. That's the beauty. Then you just need really powerful computers to deal with the size and complexity of the problems. So that's it in a nutshell. So here's a picture for you to consider. This looks pretty complex, doesn't it? Is this real or is it Memorex? What this is an 8 billion grid point simulation of a turbulent molecular cloud done by one of my colleagues at UCSD already 5 years ago. So this is not even state-of-the-art now. So here's the outline of my talk. I'm going to talk a little more about what Joel already introduced, astrocomputing and supercomputing. And then the second topic I inserted last night based on what I heard you saying, a little bit on computational methodology. Then I'm going to talk a bit about supercomputer technology trends. And then at the end, talk a little bit about my own work using supercomputers to explore what I call cosmic renaissance. So astrocomputing and supercomputing. Point one is that astrophysicists have always been on the vanguard of using supercomputers. Martin Schwarzschild was actually at Los Alamos during the Manhattan Project. And they were building the first digital computer called the ENIAC. And that really didn't come online in time for, you know, the end of the war, but it was there after the war, and Martin did lots of great work on stellar evolution. In the 60s, Sterling Colgate at Los Alamos, at Livermore, and Jim Wilson, my thesis advisor, did pioneering simulations of supernova explosions. And then in the mid-70s, Larry Smarr, the pioneer of numerical relativity, did numerical simulations of two black holes colliding by solving the full Einstein equations on a computer. And Larry came to Livermore in the mid-70s because his code was crashing. He came to work with my advisor, Jim Wilson, who was an expert in these sorts of things. And I had just joined Jim's lab in the mid-70s. So that's when I met Larry Smarr, and he went on to form the National Center for Supercomputing Applications, where I worked for 14 years. I wrote a paper for Physics Today 15, 16 years ago called Probing Cosmic Mysteries Using Supercomputers. And I will send this and a couple other references to Trudy to send to you now that I know what you're really interested in. This talk was put together kind of in a vacuum, and it's a little off target, I think, based on what you really care about. But I think some of these references might help give you the perspective. Now, the poster child for computational astrophysics is surely simulations of cosmic structure, the gravitational N-body problem. And here's a graphic from a famous simulation called the Millennium simulation that used 10 billion dark matter particles to simulate structure on a vast range of scales. I guess my thing is out. This was published in 2005. This chart here shows the growth in size of N-body simulations over time, starting in 1970, with simulations that had only 200 particles. The Millennium simulation is the symbol in the upper right, and that used 10 billion particles. And there's a fit to the line, but just this year, a simulation was done with 1 trillion particles. This is the first such simulation. And I know about this because it is a finalist for the 2012 ACM Gordon Bell Prize, and I am fortunate enough to be on the prize committee, have been for the last 3 years. And I can't tell you who the author is. even with wine, I won't tell you. But they simulated 1 trillion particles on what was, until last week, the most powerful supercomputer in the world. And you see that it's actually above the line. And this is because supercomputers themselves are tacking off on a steeper trajectory than they have been. And this is because of ridiculously massive parallelism. The core counts are just going right through the roof. Of course, no one, or hardly anyone, can program those machines, but these folks could. You could tell exactly the same story about fluid turbulence research. Here's a figure out of a Gordon Bell Prize winning paper 10 years ago already, simulating fluid turbulence in a box. So that's the computational side. It's just, you know, we've had an embarrassment of riches for decades, and it's still going if you can only figure out how to program those machines. I mean, I will say one of the problems is fewer and fewer of the practitioners in a given field know how to program these machines. And so this is why community software is so important. Otherwise, the rest of the community is left at the curb. And this is why 30 years ago now, I decided to spend my career developing community software, because I couldn't do all those interesting problems myself. Let's turn to the data side. Astronomers have always been at the vanguard of digital data explosion, and one of the reasons for that is radio astronomy is born digital. That data never hit a photographic plate. So that drove digital astronomy. And then, of course, space astronomy, all that data has to be digitized to be sent to Earth. And now ground-based astronomy is digital, Sloan Digital Sky Survey. Here's a slide on that. It's sometimes referred to as the Cosmic Genome Project. It is 2 surveys in one. It's a photographic survey and it's a spectroscopic survey. The data is all public, over 1 trillion pixels of image data, 40 terabytes of raw data, which expands to over 100 once processed, 5 terabyte catalogs. Everything is in the terabytes, which is still at the edge of what we can deal with easily. In fact, I would say that terabytes is, until Gordon, beyond the edge of what we can deal with easily. But where is this all going? Just look at the number of pixels in the focal plane array. 120 million pixels on that telescope. Pan-STARRS, that Joel mentioned, has a 1.4 gigapixel camera. And LSST, which should be operational by the end of this decade, will have a 3.2 gigapixel array, taking pictures of the sky every 20 seconds. Boom, 32 gigapixel, 3.2 gigapixels. Every 10 seconds, I think. Boom, boom, boom. So you can see this exponential growth in this diagram here. This is a log scale on the y-axis. This is years on the x-axis. And what you see here is the exponential growth. So on a log-lin plot, an exponential is a straight line. So these are basically straight lines with some wiggles. So the black points are the number of pixels, and you can see that's been growing exponentially. The red triangles are the number of galaxies in the surveys that these instruments are devoted to. And you can see that that is just now crossing the 1 billion galaxy threshold, and it's headed on up to 10 billion with LSST. So enormous data sets in one field of astronomy, namely cosmology. Okay, so this is the section that I hastily assembled after I heard many of your comments last night about, yeah, but how does all this simulation stuff really work? Should I believe it? It's not something that we talk about at astronomy meetings, no more than we talk about how a telescope is made. I mean, there are specialist meetings, you know, of the optical engineers where that sort of thing is talked about. And there are specialist meetings at computing society meetings that I go to where we talk about the simulation methods. But astronomers basically just want to get the science result. So I'm peeling back the curtain a little bit here, just a little bit. Now, I'm going to have Trudy send you a paper that I wrote for an obscure conference proceedings 15 years ago, 1997, entitled Computational Astrophysics, the New Astronomy for the 21st Century. And it was, I mean, it was not new to me 15 years ago, but it was new to the consciousness of most astronomers 15 years ago. And I was in that sort of evangelical phase of my life that you often find in your midlife, you know, you're sort of a man in full. Now I'm just trying to, you know, keep the money coming to my center so it doesn't collapse. So I have other concerns, but this might give you some understanding of what the business is all about. This diagram shows the synergies between observation, theory, and simulation. And it's true for any field of computational science. But here I've illustrated it for astronomy. So you have the oldest discipline, observational astronomy, which drives the development of theoretical astrophysics, whose job it is to formulate hypotheses that in the old days were validated through more observations. But the problem is that the theories are so complicated that they don't admit simple solutions. So here's where computing comes in. If you have a theory that's too complicated to solve, you formulate it as a computational problem, you solve it using computational astrophysics, that gives you a realization of the theory, which you can then look at from a theoretical perspective. It also gives you realizations of the things that you're modeling, and you can post-dict what you were looking at in the first place, or if the model is really good, you can make predictions. And if those predictions are borne out by observations, you win the game. Now, the observations pose the validation on the correctness of the model, which, you know, derives directly from the correctness of the underlying theoretical model. So this is this virtuous triangle that you see going on in all fields of computational science, not just astronomy. And this is why computation is called the third methodology of science, alongside the traditional observation and theory. Now, this is a slide I made last night to show you how the sausage is made. There is a tremendous amount of professional, you know, high-quality engineering that goes into doing all of this, but we don't talk about this. So this is the pipeline. At the top, you have a mathematical model, which typically simplifies the problem, either because you don't understand the problem well enough, or you don't want to take on such a big challenge. Then you have to make a consistent numerical representation, and this is the domain of numerical analysis, which is an entire field to itself. In fact, it's a huge field. And the word consistent means that in the limit of infinite resolution in space and time, the solutions of those numerical equations converge to the solutions of the continuous equations. Then you have to implement that in software, and you have to verify that you did that correctly using software engineering best practices, which is a whole discipline. Once you've done that, you get to run this code, and you do what's called validation against either analytic solutions of the underlying theory or against experimental results. And this has exploded into an entire field of science. And then finally, once you've done all of this, you get to apply this simulation to a problem of interest, and then you become more like an experimentalist in that you have to design your numerical experiment cleverly so that once you get the answer, you might learn something. Finally, you get some data and you do scientific analysis. And in the old days, you would loop directly back to the mathematical model because you would find that there was something missing. Or maybe the computers became powerful enough that you could add that next piece of physics. Well, these days, there is a new block here called sensitivity analysis and uncertainty quantification. This, in particular, is being driven by the nuclear weapons laboratories, Livermore in particular, because what you really want to know is how confident can I be in those results? And that requires running thousands of these simulations, varying the parameters a little bit and seeing how sensitive they are. So this is becoming an entire discipline in and of itself. Altogether, there's a half a dozen disciplines with their own journals, their own methodologies that have to come together in order to do this well. And I would say that not every numerical astrophysicist does all of this. I strive to do all of this because I like to do good work, but there's an overhead to that. Back to the old paper, progress in numerical astrophysics tends to be represented by a point that's moving out in this three-dimensional space. One of the dimensions is the spatiotemporal resolution from low res to high res. Another is moving out in terms of the number of dimensions being simulated. And then a third axis is the physical complexity from what I call monophysics, a single equation, to multiphysics, many equations coupled together. And I would say that my career could be plotted as some kind of path in this space. That's the way I think about what I've done. Here's a few examples showing the effect of increased resolution. I think this is now all totally intuitive to everybody because of digital cameras. We all grok pixels, and we know that the more pixels we have, the more realistic the thing looks. Same thing with computations. So this is a calculation that we did almost 20 years ago of a shock wave hitting an interstellar cloud. And what you see here is a sequence of calculations with more and more grid cells on the radius of the cloud. That's what this means, 50 grid cells on the radius of the cloud. And what happens is when that shock hits the cloud, it pancakes it, and then the fluid flow around the edge creates fluid instabilities that you can see here. Now, at this point, let me address this question of, I know I'm not going to get through my talk because I love just extemporaneizing, but let me address this question of, can I believe it? What do we learn from this? Well, there is total agreement that when you hit a cloud with a shock, it flattens, right? We've learned that with confidence. But there isn't total agreement on, how deep is this little bay at the corner of the cloud. So a simulation is reliable for certain questions and unreliable for other questions. And the trick of the whole thing is knowing what questions to ask and which are, off limits because they're at the limit of what you can say. And this is, of course, what's underneath the whole climate simulation business is they focus on one metric, Effective additional physics. This is a cloud that has no magnetic fields running through it, and this one has magnetic fields running through it. And although there are subtle differences, the cloud still pancakes when you hit it with a shock. And then if you go from 2 dimensions, like those simulations, to 3 dimensions, you see some of the things are the same, but in detail things change. You've got turbulent motions behind the shock that create a mixing cloud, which you don't see in the other simulations. And so, again, the cloud gets flattened by the shock, but in detail, it's slightly different. So this is the final figure from that old paper that I want to leave you with. What is the contribution of doing numerical simulations? And it really, so this is model maturity on this axis, and this goes from low to high. In the beginning, you're just looking for physical insight. Richard Hamming, 50 years ago, said the role of computing is insight, not numbers. And this is why, astronomers have been simulating because we really don't know what we're looking at. So you make a guess, you make a model, you simulate it. Does that look like what I'm looking at? And you iterate that way. As you do that, you're making observational contact, and the goal is to post-dict, to come up with a model that looks faithfully like what you're looking at in the sky. And once you reach this point, you've more or less got all the relevant physics, and then you can go off and make predictions. And if those predictions are borne out by future observations, I claim you've made a discovery in the computer. And after I wrote this paper, I was fortunate enough to make a discovery in the computer, which I'll be talking about at the end of this talk. Trends in supercomputers. I'm going to go over this rather quickly so I have time to show a little science. So, until last week, this machine at Oak Ridge was number 3 on the top 500 list. 220,000 compute cores, 2.3 petaflops. This is the computer I use for some of my simulations of reionization. This machine was number 1 on the top 500 list 2 years ago. Again, until last week, this machine in China was number 2 on the top 500 list, Tianhe 1A. It is a hybrid CPU-GPU cluster with almost 5 petaflops of peak speed and 186,000 cores. And this made a tremendous amount of news because, China's going to eat our lunch, that lovely journalistic chestnut. And that was number 1 about a year ago. And then Japan came on with the K computer, which until last week was number 1. You see the thread of this story? 700,000 compute cores, but these are good old-fashioned CPUs, 8-core CPUs, clocking at 2.5 gigahertz, and with over 11 petaflops peak speed. And then last week, the big news coming out of Hamburg was that US retakes the supercomputing crown with 16 petaflops Sequoia. It's actually 20 petaflops, and it's right across the bay at the Lawrence Livermore Laboratory, part of the HiPACC consortium. But look at this. China promises 100 petaflops by 2015. So supercomputing has turned into an international arms race. It's a source of prestige, and power and glory. Now, they actually all look the same. They're just rows and rows of racks with cables. But what's going on the inside is what's changing. So here's a few graphs showing the growth in the peak speed of the #1 supercomputer over the years. This is all taken from the top 500 list. And normally we plot this on a log-lin scale where the exponential looks like a line. But if you plot it just lin-lin, you can see this, the singularity is near effect, where whoom, everything takes off with this exponential. So we're now up to, well, Sequoia is actually supposed to be 20,000. I think they only had a piece of the machine. But, so there's Sequoia. There's the K computer. This is actually a smaller version of Sequoia at Argonne. And there's the Tianhe 1A. This is the number of cores. And again, on a linear scale, it looks like we were doing nothing until 2005. This is exactly what Joel was talking about. In 2005, the clock rate leveled off, and what the vendors started doing is going into multi-cores and pumping up the number of cores per processor. And so you saw a bump there, and now with GPUs and other many-core processors, the total core counts are going through the roof. The Sequoia is the first machine with more than 1 million cores. Significant threshold. Now, like I said, I've been on the Gordon Bell Prize Committee for 3 years running, and we get 30, 40 applications every year, and we have to winnow those down to like 5 finalists and then 1 winner. And it was really interesting last year. The finalists were using all kinds of computers, but the one thing they had in common is they were using a lot of cores. So you can get cores in many ways. They come in many forms: multi-core CPUs, many-core CPUs, GPUs. You access them differently, which means different ways of programming. You can access them directly on the compute node or as attached device. But in the end, it's just cores. It's like bullets, How do you win a war? It's bullets. And so the hardware vendors are throwing a lot of cores at the user, and if you can figure out how to use them all together, you can do great things. Now, this is a really interesting plot, and it tells you quite a bit about what is really going on. What this is gigaflops per core. And this doesn't look like any of the previous slides. You see down here, then boom, down, up, down, up, down. What is going on here is a battle royale between fewer powerful cores, like in the K computer. Those are SPARC 64 processors, battling with more less powerful cores. These are like the Blue Gene machines. And this has seesawed back and forth over the last 5 years or so as different kinds of computers have taken the top 1 spot. Now look at this curve here. This is a fit to this thing, and what you see is that the gigaflops per core is going up, which generally means more energy, which is also what Joel was talking about. So here is the actual power. This is total power of the top 1 system in kilowatts. So this is 3.7 megawatts, 7.5 megawatts. So this point here, that's the K computer, 12 megawatts to power that bad boy. And that trillion particle N-body simulation was run on the K computer, the full machine. So you can think about that. It took 12 megawatts for probably a week to simulate the universe at that scale. What's the power bill for that? The significance of Sequoia is it's a low energy solution. It's of a product line called the Blue Gene line from IBM that is well poised to take us even further. A few years ago, DARPA did a study on what it would take to get us to the Exaflop, which is 1,000 petaflops by the end of the decade. And even under the most optimistic scenarios, the energy costs exceed 100 megawatts to get us there. And so the thing about Exaflop, which is the thing that us high-performance people talk about a lot, is it's going to be constrained by energy. Okay, so let me talk about the data side a little bit. Trudy, are you the timekeeper?
Yes.
How much time do I have before my 45 is up?
Yes, before the 45 is up.
Okay. Gordon, there it is. You've seen the picture already. And Joel has told you that it has lots of flash. What's the idea behind Gordon? One is that the data, which is stored in memory or on disk, keeps getting further away from the processor in terms of the processor speed. And the thought was, do we need a new level in the memory hierarchy? Number two was data-intensive applications. The actual programs themselves may be sequential, we call them serial, or difficult to parallelize. So wouldn't it be nice if we had a large shared memory machine rather than programming 1,000,000 cores? Couldn't we look at all of that as a shared memory machine? And so we were able to do that with the Gordon design. We filled a gap in the memory hierarchy with flash SSD, and then we used special software to extend the shared memory programming space over all the memory of the computer, and even possibly to include the flash. So what that looks like is you take a bunch of ordinary compute nodes that you would make a cluster out of. You add a couple of other units called I/O nodes where you put all that flash, and you wrap all of that into a big shared memory programming environment. And to the end user, to the application scientist, a supernode looks like you've got 8 teraflops of compute, 2 terabytes of memory, and 10 terabytes of flash. And the full Gordon machine is 32 of those. So 32-way supernodes is the full Gordon machine. So I guess I knew I wouldn't have time to talk about the science, but would you like me to talk for 5 minutes about the science and then ask me questions for 10 minutes? Would you? Okay. All right, so I have my mandate, Trudy. So what I do with all this computer power is work on the cosmic renaissance. You've probably all seen diagrams like this: Big Bang, inflation, formation of the cosmic microwave background. Then there is the dark ages, where there are no luminous objects in the universe. What follows the dark ages is what I'm calling cosmic renaissance. It's the first billion years until we have the first galaxies. If we flip that diagram vertically, now the Big Bang is at the top, time runs down, and there's really 3 interesting chapters to the Renaissance: the formation of the first stars, the formation of the first galaxies, and then the reionization of intergalactic gas, making the universe transparent, which is what allows the Hubble Space Telescope to look all the way back to that curtain. So one of the discoveries that I was fortunate enough to make with my students in a computer was how what the first stars are like. And here's a rendering of that simulation. And we just asked the question, if large galaxies form through the merger of smaller galaxies, where does all of this begin? Where does the River Nile start? You know, we just wanted to trace the watershed all the way up to its starting point. What kind of object is formed and what is their significance? Well, this work was fortunate enough to be selected for the cover of National Geographic, the first computer graphic in the history of the magazine, February 2003. And we used what many of us call universe in a box simulations. I don't have time to go into the details, but the nice thing about cosmological simulations is that they are a well-posed initial value problem. Observations give us the initial conditions. This is the cosmic microwave background fluctuations observed by WMAP. You can read off the power spectrum of these fluctuations and put them in a box and evolve this forward in time using known laws of physics. So that's the short version of numerical cosmology. So let me show you what that looks like. Well, we know that the universe is dark. Yeah. That's okay. I think you can. This is a little chunk of the universe that's being simulated forward in time about 1 billion years. And these little dots are the first gravitationally bound objects that form from those initial fluctuations. And then, using a special technique called adaptive mesh refinement, where it's like you have a hierarchy of grids of finer and finer resolution, we were able to zoom in on one of those and see what was going on in the center. And what forms is a protostar with a mass of about 100 times the sun. And so that's a range of scales similar to zooming in on a building from Google or Google Map. So I will skip the movie and just tell you what the implications were. The first stars are massive. That means they don't live very long. They live a few million years. They blow up. We found that only one star forms per what we call a microgalaxy. These stars are extraordinarily luminous, and they photoionize the intergalactic gas. And because they're massive, some of them will explode as supernova, seed the universe with heavy elements, which of course are essential for the formation of planets and life and us. And then in my last -1 minute, I'll just say where we are right now. We are working on pushing all of that forward to make the first galaxy, which you could consider a protogalaxy. The first galaxy forms out of the debris of 100 to 1,000 of those things that I just talked about. The heavy elements produced by the first supernovae allow the gas to cool faster and produce the first normal stars. Radiation from the first galaxy, stars and galaxies, ionizes and heats the intergalactic gas, and that ionized and chemically enriched gas gets ejected into space. And all of this needs to be simulated over a vast range of scales because you cannot ignore those first objects because they are the seeds for the first galaxies. So I'll just show a few animations and then sit down or take questions. So this is from a paper that was just published in the Astrophysical Journal by John Wise and myself. And this is, each one of these little red dots formed its own first star, And you can see how they're blowing up. Those are the supernovae that are blowing up those little halos, as we call them. And so what's coming together here is a galaxy about the size of the Small Magellanic Cloud, but it's doing so at very high redshift. And if you look at the temperature of the intergalactic gas, you can see all of the ionizing radiation and supernova explosions that are happening as this first galaxy is assembling. It's extremely violent. And then here is what comes out. This is that circle envelops what we are calling the first galaxy. It's not a pretty looking thing. It's blobby. These are individual star clusters that have been formed in this simulation. And as I said, it's about the size of the Small Magellanic Cloud. You can see supernova remnants. Supernova have blown holes in the gas. And eventually all of this will come together and form a more massive galaxy. So I better just stop and just run this animation. This is a broader view of the patch of the universe that we've simulated. And this is what the first billion years looks like in the history of our universe. It's a lot of fireworks, a lot of complexity, but with the power of the computers that we have now and are getting in the future, we should be able to form the kind of galaxy that we can see with the Hubble Space Telescope now. So I'll stop there and take questions. Pardon me? This is actually the radiation this is the ionizing radiation from these massive stars creating ionized regions, heated regions around themselves. Those first stars don't live very long, a few million years. So they're formed, they radiate, they ionize, they die, you get recombinations. It's sort of a fireworks effect. Okay, so there's plenty of time for questions, I hope. Start with you, yeah.
So you said sometimes that astronomers don't talk about any of the back end stuff in the supercomputer. So we were talking about we don't know how to trust or when how to believe when or don't know how to know when to believe what comes out of the black box. Because it's a black box for astronomers too. How do you kind of then decide what is a good simulation or is it just
Yeah, she said, since we don't talk about the methodology to astronomers, how do astronomers know what to trust? And it's an education problem that you can't solve directly. You can lead by example, which is what I've done. Part of the section that I completely skipped over was the business of software development and software verification and software validation. You test your code against known solutions in what is called a test suite. These are a collection of standard problems that any code of its type should be able to pass. And typically these test suites just grow in size over the years. And so now, you test the N-body dynamics against a certain set of tests. You test the hydrodynamics against another. And nowadays, if you want to talk in front of an audience in an informed way, you better be able to answer questions about what test suite you compared your results to. And this looks like, this is everything in the kitchen sink. How could you possibly believe any of this? But there's probably, there's like 4 or 5 main physics modules interacting here, and each one of them has 6 to 10 tests that we do. And then you put it all together and you do something, you simulate an object and you do what's called a resolution study. You see how robust your results are to changing the number of grid cells, the number of particles. And that's all sort of, you keep all that in your back pocket in case someone asks. And you publish it, yes. The papers are filled with all that detail. Yeah.
You talked about how some of your first star simulations are based, where you use the CNV data as kind of a starting point for that. Early on in your talk, you talked about a shock wave hitting a molecular cloud. You're making some, what kind of assumptions are made about the initial density, the uniformity of density in that cloud?
Of course, that's an idealized problem, and no cloud like that exists in nature. And
so it's the assumption that it is uniform density?
yeah,
Right.
it was a theorist's interstellar cloud getting hit by a perfectly planar shock.
Yeah.
And that's because you're looking for insight. You're not trying to model a specific cloud in Orion. Yeah.
Talking about the Sloan Visual Sky Survey, point you said that 40 terabytes of raw data, 120 processed. What does it actually mean? What's the difference in the data that's been crunched versus raw?
Well, a lot of it's image data, and it comes off the camera in a uncalibrated form. And so there is a step, I mean, I'm not an observer, but I hear them talk, flat fielding and this and that, and flux calibrating. And so you have to, it's not like your digital camera that produces you a beautiful image right off the bat. It's not perfect, and it needs to be corrected for imperfections. Yeah.
So one thing you said that was very helpful, that the don't panic slide with all those equations. Ultimately, how do you formulate those questions? Are we still trying to answer the same questions now that we were asking 50 years ago or 40 years ago in terms of those equations? Are we just getting more and more detail of these same questions? I guess, how do you know?
Yeah. Well, science is a frontier that always expands. And so the top level questions haven't changed, like how do stars form? What makes a supernova go bang? How do we make a galaxy? How do we make the Milky Way? Those big questions, but the level of detail at which we're asking those questions has advanced enormously in 20 years. I would say 20 years ago, to a large extent, we were still groping at the fundamental physics that we should include in the model. I would say, by and large, we now all agree on the physics that's required for topic X, and we're trying to do simulations of higher and higher fidelity that by now actually capture the gross phenomena. Like that simulation, the Memorex picture I showed. Statistically, that's identical to observations of molecular clouds. So then you go to the next level of question that the observers are asking, because they've already bought off on the fact that you basically check that one off. So it just keeps on going to higher and higher levels of detail.
And I guess that's what gets challenging. I don't, from a journalist point of view, it's hard because ultimately, yes, some of us are interested in the technology itself, but a lot of it's motivated by the question.
Yeah.
And if questions are only kind of being tweaked, or we're looking for more resolution, it's a harder story to sell against our editors.
Yeah. Well, take star formation. When I was a graduate student, everyone understood just instinctively that gravity drove star formation. Makes sense, right? The current paradigm is not that. It is turbulence drives star formation, and gravity finishes it off. And probably Mark Krumholtz will spend, Mark, there he is, yeah. I think Mark will address that. So the paradigm has actually shifted completely.
Also with these first stars,
Hundreds of solar mass.
That's not fair.
It's thought that they're.
No, but, I mean, just to give you a sense of how uncertain this is, first of all, you should understand that this theory that Mike's completing my theory, I'm as much as anyone to be able to come for well-standing behavior here at Santa Cruz. But it's quite uncertain. If the dark matter is supersymmetric gas, in certain ranges of ground space, the first stars are going to be nothing like Mike simulated, Mike and many other people. They'll be powered by the annihilation of the dark matter. It'll completely change the picture. Until we can get some direct evidence by comparing these beautiful simulations with fabulous observations that are going to be possible with the next generation of radio telescopes like the Square Kilometer Array, we aren't going to know if this stuff is true. It's not just tweaking at this stage. We have never seen anything like these first stars. We haven't even seen the output of the first stars in the form of the particular pattern of heavy element generation that first stars that are really quite massive would make. So we have no direct evidence that any part of the story is right.
Yeah, which is why we have to actually truck ahead and make first galaxies, which themselves are too faint to be seen by Hubble. And then out of these first galaxies, we have to truck ahead and make the first really massive luminous galaxy, which has been seen by Hubble.
But we'll have James Webb Space Telescope both in 2 years.
Yeah.
And then we can go back and actually see some of this. But that's why we need things like James Webb Space Telescope. Don't imagine that this is true. It's a great story.
It's a prediction based on known physics. I'll go back to you since you already asked the question. Yeah.
So, in answer to Chad's question, you said that we know that turbulence drives star formation, gravity, which is not. What's the equivalent physical insight you gain from this vast increase in resolution for large-scale structure?
Well, I'll try to answer that succinctly. Well, we know that the theory that Joel invented, the cold dark matter theory, it accounts for large-scale structure and clusters and galaxy structure all the way down to about a megaparsec scale. It also makes some predictions on smaller scales that may or may not be seen in nature, and that is, you know, a part of the lively conduct of science. Things having to do with the cuspiness of the potential in the centers of galaxies, the number of dwarf halos, dwarf galaxies in the local group. These are all predicted by the CDM theory that don't exactly line up with observations. James Bullock will be addressing that in much more detail, student of Joel's. But I would say that the universe on the largest scales is beautifully captured by the CDM theory. But once you get into the realm of what Dick Bond calls gastrophysics, things become murkier. Yeah.
Is there a line between discovery and prediction? You said you made discoveries through simulations, but then it seems that ultimately all these simulations are going to be held to, can we observe this? So can we make discoveries with simulations, or is it just more about we need to know what we're looking for?
You know, that's a great question. I think an observer would never admit that a discovery could be made except through empirical means. I think that's what the word means to them. I disagree. I think theorists and simulators can make discoveries. A better example that actually I was a part of in the mid-90s was, what is the physical nature for something called the Lyman alpha forest? This is a thicket of absorption lines you see in the spectra of distant quasars. And it turns out it's a direct consequence, again, of Joel's theory of cold dark matter, which clusters in the universe, forming this cosmic web. And what I and others did was we added the intergalactic gas, and we asked how would it absorb the light from a distant quasar as that light came to us. And it turned out that the statistical properties of that absorption was exactly what was seen in every respect to, let's say, 10%. And so that was a discovery of the physical nature of an observed phenomenon based on a theory that was just applied to that context. Now, that was 1995, 1996. What's happened since? What's happened since is, so that established the paradigm that we all work in. What's happened next is going from the 10% level to the 1% level. And that's where you get into all kinds of interesting new physics. What we found is it doesn't agree to the 1% level. What's the source of the discrepancy? Could it be the gastrophysics that we're not doing right? Or could it be that the dark matter itself isn't exactly cold? Is it warm dark matter? Or is it a mixture of warm and hot and cold dark matter? Is it sterile neutrinos that George Fuller will talk about? There's this lovely coupling between observations, astronomy, and fundamental physics in cosmology that I think is why we all love to do cosmology. Maybe it's annihilating WIMPs, putting a little bit of energy into the intergalactic medium. Maybe it's primordial black holes that none of us have really taken into account in our models. So there is that possibility. So what I want to say is first you don't know what the heck you're looking at. Then you have a paradigm, and that paradigm works for a while until the measurements get so precise that you start seeing little tears in the fabric. And at that point, don't despair. Rejoice, because that's an opportunity for discovery. Yeah. Yeah.
Could you compare the supercomputers that you're using to make these simulations with, say, this laptop? Like, how much more power are we talking about?
That's your typical dual core, 2 gigahertz, 4 flops per clock chip. So that's probably got about 80 gigaflops. I would say 80 gigaflops. This was done on, I was talking about her laptop. Oh, that's right. No, I was thinking of an 8-core processor, yeah. So maybe 15, 20 gigaflops. This is running on 4,000 processors, each of which is probably 4 times as powerful as your, so what is that? That's 16,000 times. And this is a small calculation. This is a tiny patch of the universe. I didn't have time to show the results from a simulation with all this physics in a big patch of the universe that eventually will form a first bright galaxy. Yeah.
Silly question. What's a flop?
Floating point operation per second. It's an add or a multiply. How many adds and multiplies you can do in a second? That's not a silly question if you don't know.
I've got a wacky question.
Yeah.
So are people talking seriously about building supercomputers out of superconductors that would solve the energy problem?
No, I haven't heard of that. That would be great.
But our modern transistors require, they wouldn't operate at low temperature.
That's a good point.
Completely new kind of technology.
That's it.
What about just the interconnects?
You know, it's no, short answer. But they are talking about some really fabulous things as the follow-on to CMOS. And this is carbon nano. You've heard of carbon nanotubes? Imagine just a little sheet that looks like chicken wire, you know, where you've got the little hexagon. So it's a carbon nanosheet that becomes the substrate for making the gates. This is a top candidate for being the, and that operates, it operates in the totally quantum coherent limit, meaning there's essentially no resistance. So you have essentially what you want with superconductivity, which is low resistance and low energy dissipation. But it's not cooled. It's just because it's so thin, you can only get, one wave function fit in there.
Mike, just one quick question. I noticed, and I think this is something that needs to be aware of. It could be a long time, a few months after joining HiPACC to become aware, that astrophysical, computational astronomers and astrophysicists use the word data to mean two things, two very different things, not just one. We tend to think of data as being observational data that gets crunched on and get results. But in the case of simulations, I've also heard simulators talk about getting data out of what they crunch.
Yeah.
So I'm wondering if you could maybe clarify or address that.
Sure. Perfect shill. Yeah, so one of the most prodigious sources of data are supercomputers themselves. And because what they do is they create a 4D movie of whatever you're simulating. This is a slide I skipped over. This is the growth of my own cosmological simulations with time. So there's the year, the number of grid cells, the number of cells in billions, the number of CPUs I used, and the machine I used. So from 1994 to 2010, I went from 1/8 of a billion cells to 1/4 of a trillion cells. And in problems, this is an increase in problem size of 2,000 in 16 years. And if you work it out, that's a doubling time of 1.5 years, which is just an illustration of what we call Moore's law for supercomputers. And this is no accident, because I told you at the beginning of my talk that what I do for fun is I ride that exponential, and I have my entire career. Point is, these simulations, every snapshot that it writes is 30 terabytes, essentially the size of the entire Sloan Digital Sky Survey, done over 20 years, I write out at a snapshot. And then I do it again and again and again. I have 2 petabytes of data stored at Oak Ridge from this simulation. How do I analyze it? Well, short answer is build Gordon. And so the truth is, my simulations are too large to run on Gordon. But Gordon is a perfect workstation to analyze the results of those simulations, and that's what I use it for. Yeah.
What Trudy said was really helpful, and when you had that slide about the synergies between these 3 different parts, I was thinking this looks like a really dynamic process between data and knowledge. And in social science, we'd say it can be a dialectic. There's knowledge off of the data and data off of the knowledge. And I was wondering if you can think of any times that, or describe the effect of treating data as knowledge, or treating knowledge as data in the context of what you do. Is that just
Well, I mean, in what is now being called data-enabled science, which is sometimes called the 4th methodology of science, but I resist that. I would like to lump that into the 3rd methodology and call it computational and data-enabled science. That's what the National Science Foundation calls it. They don't want a 4th methodology. That means they'd have to have a 4th division funding it. So anyway, whether you call it the 3rd or the 4th, within that data-enabled science paradigm, we talk about data, information, knowledge, and it's a pipeline. Data is just bytes written on a storage medium. Then you have to convert that to useful information. So when you see something like this, that conversion has already been made in a rudimentary form. Make an image of it. That takes a lot of processing to do that. And then even this is not knowledge. It's the point at which you can start asking questions in hopes of getting knowledge. So that is a process that involves a series of steps, and you need powerful computers on which to do that. And that's what the Gordon machine is it's a supercomputer that can take in the data from wherever, from observations, experiments, simulations, and speed up the conversion of that to information so that in the end you get knowledge. That project, I would say, we just went into production in February. We're funded for 4 years. Remains to be seen how much knowledge we generate, but so far, so good.
I'm going to have to be the heavy here.
Yeah.
This is wonderful, Mike, and you're such a clear explainer.
I'll be around until tomorrow afternoon, so plenty of time to ask me follow-up questions.